Okay, so this is going to be a VIP talk because obviously there's not so many of you guys. So good afternoon, and thank you for joining me here in this talk at NDC. It's my first time here actually, and pardon me if I'm a little bit kind of like not very at ease. It's because it's been about like 8 years since last time I gave any talk. So with it, I'm hoping to share with you some of what I have learned so far working in this software industry. Working on shipping different products and services. So a little bit of background here about myself. I think I was about like 14 years old. I'm 36, so that's about like 22 years ago when I built and shipped what I consider my first product. It was an intranet document sharing collaboration thing that I built using the tools I had at the time, and encouraged by my own father, I tried to sell it or license it to an insurance company. I'm aiming kind of high. The software was PHP and MySQL. That's basically what we could use. That's what I knew how to use as a 14-year-old kid. The CEO was rather thrilled. Cheap, works, exactly what he needs. The IT guy hated me. So, and later I understood why. I mean, I'm from Morocco, Casablanca. That's basically why I try to do all of these things. And he was convinced that I stole the software. What he didn't know is that I just used the tools that allowed me to ship, to make a product very easily as a teenager. I got rather angry, so I just uploaded all of this software in one of those online forums we had in the late 90s, early 2000s. This is basically around that time that this happens. And that I just discovered licenses, slapped a GPL license on it, put it online, and that was my encounter with free and open source software. And believe me, it has shaped me for the rest of my life. But that's another story. So why am I talking about all of this? You might be wondering. It's because for a very long time I really thought that I was passionate about software, about writing software, where in fact I wasn't. The thing that really motivated me and made me driven was the answer to two questions. How do we build software? And how do we get to use it? And I'm hoping today to converse with you and try to find an answer for the first, which I've been trying to figure out for a long time. And Erlang has shaped my view on this. That's why there's Erlang in the title. And I'm still learning these things. Anyway, before I continue, short introduction. Beside the background, my name is Sabil, as you can see over there. I am the managing director of a small service company based in Stavanger. We do kind of software development, a lot of embedded, high skill, whatever kind of, strange things you might find difficult to deal with, you can pretty much talk to us. Some of these things we solve using Erlang and Elixir, by the way, but it doesn't have to be. Anyway, the first thing I want to talk about today. So if you're here expecting to see a lot of Erlang code, please, I'm sorry. The first thing I want to talk about today is software, or rather software engineering as a discipline. If you look at software, it's rather in this messy, contradictory, I would say paradoxical place, where about how we want to build it and about how we get to use it. On one side of the spectrum, we want our software to be tidy, clean, pure. I am a supporter of that. I love functional programming, I love immutability, all these things. We don't want side effects. We essentially want our software to live in this ideal world and pretend as if the real world never existed. Doesn't matter, it's just software, right? And it's rather normal why we want it this way, because that's what allows us to reason about it, allows us to find its failures, its faults. On the other hand, we have to have our software running in the real world to represent and interact with this real world. And the question I want to ask is, how do we get both? Anyone? No? Okay, I'll try. The scientist's answer is, let's build models. Let's build models, design our system, and the more messiness of the real life we have to take care of, the more advanced our models get. That is the scientific way of looking at it. So incorporate the messiness of the real world into our models. The problem is, it doesn't take long before it gets way too complicated. I think that's my understanding of it. Again, this is kind of my thoughts I'm sharing with you here. The engineer, on the other hand, they would just take some duct tape. I'm an engineer, by the way. And they would just say, well, you know what? This is good. And we can add the idea of compromises next to it. Let's compromise on this. Let's compromise on that. I would go one step further and would say engineering is not about compromises. It's about calculated compromises. And that's basically the fundamental difference here. When I was a young engineering student, my favorite topic was not computer science. It was physics. And I guess for now, I don't see anyone that I know from before so much here, but the ones that know me would be rather surprised about that fact. And the first thing we had to deal with, the first lesson of the first year when I joined engineering, was this: quantifying errors. That was the first thing we had to understand. And it starts with this fundamental idea that errors are inevitable and immeasurable. And we just have to accept them for what they are and learn to live with them. Once we accept this, it comes down to quantifying them. Quantifying these errors, basically, with the objective of really understanding them and how they affect, on physics, the system you're observing, engineering, the system you're building. What's fundamental again here is that we have no real way of measuring errors directly. We just don't know them. We just know that they're unknowns. We have to deal with them. Because if we could measure errors, they wouldn't be there. We could only approximate them. We have an order of magnitude. And this here allows us to use the simpler models in our systems, in our designs, and get away with it. I think we have a lot to learn from experimental physicists, which is the ones I studied under their supervision. And because they have spent a considerable amount of time, energy, resources on figuring out how to consolidate the real world, the one where our software actually lives, surprise, with the abstract world, the one where we want it to live. I think that we still have a little bit, I mean, I like science, but maybe we have a little bit too much science in our field, and too little at the same time. It's kind of a strange setup. And in the software industry, I think we should do what physicists have understood. There is no point in fighting reality. So let's stop pretending it doesn't exist. You might disagree. That's my perspective on things, and I respect that. We can talk about it later, but that's how I see it, really. And I think I would say it's about time we acknowledge the real world and that it exists. I mean, the funny thing is that if we really look at ourselves, like, we managed to convince a few billions of people that they should put their lives online and that they should be on Facebook and Instagram. We just brought their lives with us into our world. And that basically defines how we perceive the world. As computer engineers, as computer scientists, we always want everything to be digital, because it's simpler, because it's easier. I mean, metaverse or whatever VR stuff. I think something is very wrong with us. incorporating the real world into our way of seeing things and thinking is probably something we should consider seriously. That will allow us to understand the errors we do and the errors of our system, quantify them, and just accept them instead of just reject them and say they just never exist. They never happen because my model is proven to be correct. Yes, it is proven to be correct inside of your system, not outside of it. Just to make this clear, I'm not saying that basically we should outright reject formal verification. We should outright reject static, strong typing. Not at all. I think we need those things. They're brilliant, they're wonderful tools. But we need more on the outside. And what I'm arguing here is that we need to better understand what other engineering disciplines have understood. Failure is an inevitability. I guess computer engineers, scientists, you read papers sometimes when you find them interesting, right? There's probably a gazillion paper on software failure, and fault tolerance. There's a lot. The problem is that we never read them, or we never understood them, or we never put them in practice. We do in some fields. We do. Maybe I'm wrong in talking in absolute terms, but what I'm trying to, I'm talking in a general way here, like overall, as an average of our community. I'm not talking in specific cases. There is some industries that care very much about these things, and they put all their energy into it. I'm not denying that. I'm talking about the average software industry. And I think that our software communities, in their quest of how should we write this software, have been too focused on how software is actually written. How do you write the software? And they forget about the second part. The software is not only written, it's also constructed. Like it's built. It's not just about the code you write, it's about everything around it, really. And that, by doing that, and because of our history, where do we come from? We're ignoring an entire class of errors, and that is the errors that are really hard to solve. The ones that come from the real world. Not the ones you can formally prove that never happened, because that's inside of your model. Or you have a very strong type system that will help you. All this is brilliant, absolutely brilliant. And that brings me to the next topic, the second part of this talk, software community. Actually, my favorite part of the talk, but also the most different, or the most like way out there in way of looking at the world. If you look at us as a software, we're a young field. Software engineering is relatively young. And if we look at software we have today, probably, I'm not able to give you an exact date, but I would assume it's about like 70, 80 years that we started writing software like kind of similar in the same spirit as the one we have today. I think something like that, right? Maybe late 40s, early 50s, I don't know. And in this 70, 80 years, we managed to build an ever-expanding archipelago of fragmented software communities. And these communities are just so far away from each other. Sometimes they are adversarial. They hate each other. I was here in this exact same room yesterday. I was like attending this talk, like 42 funny ways of saying hello in C. And Oliver, who gave the talk, he was like, yeah, he considered himself bilingual, and he was like, well, it's really funny because he teaches both C and C++, and he was saying like, it's really funny because when I go teach C, people assume that I hate C++ people. And when I go teach C++, they assume that I hate C people. It doesn't have to be that way, does it? How many of us have laughed at PHP? It's pretty hopeless programming. Anybody heard that one before? No? Yes? Idris? Agda? First time I was in ICFP a few years ago. That's like a functional programming conference. And I attended kind of a live demo of Idris, and I was just like, whoa, this is brilliant. So I just have to write the types and the program kind of writes itself. Yeah, cool, I'm not gonna use it. Any Rust guy here? Yeah. Sorry, I don't want to offend you here, but what I wrote here in my note is, let me rewrite that for you. It's gonna be safer. That's the culture. That's basically what I'm trying to get to. And to better understand these dynamics that we have, we need to introduce a very important concept called imagined communities. This is not something I came up with. This is a term coined by Benedict Anderson. This is taught in political science, and it's a very important tool in understanding the modern concept of nation states, countries, as we know them today. It's also used a lot for understanding things like nationalism, and I think it applies to us. And because after all, we're people writing software, and we build communities. So the easiest way, I'm not a political scientist, I dabble in these things. I try to understand, I try to look outside my communities, because that's really what I'm after as a person. But to understand this, the easiest explanation I could find is to try to define it in terms of what it is. What are the attributes that constitute an imagined community? The first thing is that they're imagined. I have it right there in the name. The last one is community, and there's a bunch of things in between. Today I'm in front of you trying to identify as an Erlang guy, but the reality is that I belong to so many different communities, and I have throughout my life so far, and I probably will continue moving between them because I guess I'm not loyal, I don't know. As an Erlang guy, most of the other Erlang developers are people I have never met, and I probably never will meet. I don't know. I've been to Erlang conferences, but there's like a lot of people out there. Somehow, in my head, I'm convinced that I belong with them. I'm part of that group. The second item is that they are limited. People that are outside my circle of whatever language developer, like Java developers, are outside of my community. There's a certain border in our mind. It doesn't have to be a physical border. There's a certain limit. They're sovereign. So that means they get to make their decision. Now, I'm not gonna spend time talking about like the process, the social contracts, and all these things that make the decision-making process. So this doesn't imply democracy in any way. It just means that these communities get to decide where does the community go. So the C++ community, which I'm assuming here that a lot of people you here are part of or consider themselves part of, gets to decide what goes onto the next version of C++, either by contributing or raising their voice or just using the feature before it's there. They get to decide as a community what is deprecated, what interfaces are added or removed. What are the newest best practices? I learned C++ 98, so that's the one I was taught in, right? And I think a lot of things have evolved since then. I got to do some C++ last year, and it's pretty much not the same language anymore. So it has evolved. They're communal in nature, so that's the community part. Essentially, as a member of a community, I share a horizontal relationship with my peers, with the other people, even though I never met them. There is no concept of hierarchies in the community. There might be hierarchies in the decision-making, in the sovereign part, where basically who gets to do that. But overall, everybody consider themselves as part of the same community. Let me tell you one thing. Our software community, are they imagined? Yes, no. Are they limited? If you're a C programmer, what do you think of the C++ guy? Is he within your community or outside? Are they sovereign? Are they communal? Our software communities are imagined communities. And the moment we understand that, the moment we accept that as a concept, again, this can be applied to a lot of different things. It can be your colleagues at work. It can be a lot of different things. You just have to apply this concept. But the moment you really understand it, the moment you accept it and internalize it, the moment it allows you to understand what is within your community and what is outside, it allows you to move from community to community. It allows you to transcend that community and move to another one because you never really can escape it. I initially wanted to say, you can escape their dogmas, but it's not quite. You can just move from one dogma to another. Haha, this one is even more interesting. So software communities are imagined communities that are fueled by what is known as sociotechnical imaginaries. I didn't make that up. It's real stuff. There you go. Sociotechnical imaginaries. Can you read it, or is it a bit small? Everybody good? Yeah. So Jason Off is a professor, well known in the field of technology and sociology, Harvard. She describes it as collectively held, institutionally stabilized, and publicly performed. What does that really mean? It means socio-technical imaginaries. Let me try to dissect that word. Imaginary is whatever we have in our mind. That's their definition. And socio-technical is just a term about like what type of, what category of community do we have. So collectively held is a belief, it's a perception, it's a vision of the future that we all have in our mind at the same time. They're institutionally stabilized. So that means that we have a set of norms and values about how we're supposed to do things. Best practices, coding styles. That's basically how we see it. And publicly performed. This conference here is a public performance of the C++ community. It's something that we see, it's something that you observe, it's something that people can relate to. This socio-technical imaginary, they are understood to be, I want to say, animated by what technology can do for our societies. And this imagination pushes us into pursuing the world one way or another, really. Like, it defines how we see things and where we want them to go. The thing is, limited. Our imagined communities are limited. So these socio-technical imaginaries, they tend to live within the boundaries of the, I'm talking in averages, we're not talking in precise terms here, within the community where they are imagined. And I'm here to tell you about one of the communities I belong to, and that is the Erlang community. What it has taught me, and how it has shaped my imagination about what can be done with this particular technology, and how it can be, the ideas from it could potentially be brought to other communities. That's really why I'm here. I'm going to continue a little bit, if you don't mind, because I think this is really important stuff. Might be boring, but it's really important. It's like philosophical to a certain extent. So what she does here is she tries to define the structure that is surrounding these socio-technical imaginaries. She brings in two concepts in there. One is what she calls the political theorists and social theorists. So those are basically, in our world, that should be like the community leaders. The people who have the authority, and I would go one step further and say the legitimacy to make the changes in our community, the ones that drive our community. They They participate, they create events, they deprecate functions, they deprecate interfaces, they have this kind of authority. And the collective, that's what she calls the rest of us. The people who are part of the community, but just accept things and live with the community. But you remember what I said earlier about socio-technical imaginaries is the fuel. Think of it like this, is the fuel that makes a community live. And if it runs out of that fuel, it will just die out. Because the dreams, the hopes, the vision of what technology can achieve for us, or that particular technology that we believe in, is no longer there. And I find this funny because, or rather not so funny, but is that it explains why our communities sometimes, many of them at least, it's not always true, they tend to calcify. They tend to stop evolving. They tend to kind of like keep trying to refine the same thing in the same way. Why is that? Because if you diverge way too much, if you go too far away, if you stray too far away, you're going to make that imaginary disappear because you no longer have that shared vision between all the people that are in your community. You probably remember the Python 2 to Python 3 transition. Yes? No? Anyone? That was one of those. The community was here, and the leaders wanted to change it in a completely different way. Like too far away. It caused too much trouble for people. Anybody a Linux user here? Yep. GNOME? Yes, no? GNOME 2 to 3? No? I was a GNOME developer in the previous life. And I dropped off because the transition from GNOME 2 to GNOME 3 was too brutal for me. I will let you think. I'm going to talk. What I'm really trying to get to here is that we have all these communities in our software world, and they have evolved from and towards our perspective, like how we are supposed to write and design and build and construct our software. Ultimately, that's why it is. If you remember my first question, the first one I asked, how are we supposed to write software? And we managed to build these communities because each one of us or each community has a different perspective of what that future software should be and how it should be. Another news, the majority, and I don't have any numbers here, but that's my view. Again, this is more of a, this is not a hard science what I'm doing here. This is humanities. So it's very soft. Take everything what I say and just understand it for what it is. The problem we have is some of our communities tend to be a bit unbalanced in their power structure. Our communities gravitate around the language. C, C++, Python. Languages have roots in computer science, the majority of them. So what you find is that there's a group of languages that is more rooted in computer science. There's another group of language that is rooted in engineering, the ones that are a bit messy and, you know, just get stuff done. But when was the last time you saw a computer software engineering community who has an artist as a leader, who drives the change? And this, because of our more sciencey perspective of the world, leads us into defining everything in terms of truth, because that's really what science is about. And makes us in denial, I'm maybe going a bit too strong here, of the existence of the real world in the systems we design, we tend to design. Have you noticed that the PHP, the Ruby communities, they tend to attract more scientists, more artists? Have you noticed that Haskell, Agda, Idris will pull more the sciencey people in it. Why is that? Yes. We agree. We agree. But it also has to do with their sovereignty structure. How do they evolve? Like people when they join, where do they see the language going? Where do they see this technology going? Right? One of them has leaders that are more in the scientific field, and the other one has leaders that are maybe more in the engineering field. So if you put scientists on one end of the spectrum, engineers somewhere in the middle because duct tape, and an artist on the end, you cannot start to see where this is going. I don't know how many of you have had philosophy, but science, art, you guys remember the difference. What is science and what is art? I think that our communities, they need to evolve. And they constantly need to do so, like any community out there, really like any one of them. Because if they don't, the future disappears, the possibility of a future disappears, then it just drains out. It starves. I consider myself, as I said, part of the Erlang community. I've been doing Erlang for like 12 years now, and I'm here again to tell you about it. Haven't gotten to that part, hope I will have enough time, but we'll see. I'm not hoping to convert any one of you, not at all. I'm not hoping to tell you that you should throw away everything you have done and start doing it in Erlang. I just want to tell you about what some of the things that I believe that community focused on a lot more than others. There's certain things that I feel have been like the strong focus of that community. And I'm hoping to bring some of that over here. And by doing that, I'm hoping that we will disseminate this idea of starting to build bridges. The bridges that connect all this archipelago I talked about, our fragmented, I don't want to say, adversarial communities. And I think that given the nature of our software, we should really start to think about how can we create environment where we develop software, where we can include the scientist, the engineer, and the artist, because all three of them have their place. All three of them are good at what they do. I just asked a question before I moved in here, which is like science and art. Well, science is about defining truths. That's the easy definition of it. And art is about defining the world in terms of truths. And art is about taking the world for what it is. Okay, there we go. Time to get started. So, my first real use of Erlang goes to 2009, late 2009. I was involved in another community called the XMPP community. It's a networking protocol. Everybody familiar with it? Or yeah. And one of the major servers in XMPP was written in Erlang. It's called eJabberD. So I wanted to modify it. Back then I was a C and Python guy. Those were basically like my languages of choice. I would pick those whenever I could because I knew them. I also wrote some PHP, some Vala. If anybody has been in the GNOME community, they will know what I'm talking about. And that's like a GNOME-specific language, like C# kind of thing, but yeah. And when I got to use Erlang, it really is a very simple language. It didn't take long before I just internalized the syntax and how it works. It's just like a few hours, really. And I don't consider myself a language expert at all. But I didn't know how much it would affect me in my view of how software should be built. There are many things that Erlang does differently, very differently, in fact. And when I'm talking about Erlang, I'm talking about the Erlang ecosystem. So it's not specifically the Erlang language, because the Erlang ecosystem includes other languages like Elixir or LFE, like other languages in this world. And the question that Erlang tries to address is this one. How can we build reliable software from unreliable software? Back when everybody was looking at how like software reliability and software tolerance, fault tolerance, and all these, difficult questions to answer. Many of them run in the direction of static typing, formal verification. That's the sciencey end of the spectrum. Erlang went the other way, like the total opposite way. It starts with this idea that we'll never eliminate failure. Again, engineering, I talked about in the beginning. There's no way we could get rid of failure. So the late Joe Armstrong, which is one of the co-authors of Erlang, he was a physicist. And he saw the world through the eyes of a physicist who was forced to do computers, I guess. Erlang starts with this assumption that some of you might say defeatist, and we just give up on the fact that error and failure is just inevitable, just like in the real world. And we cannot keep pretending that our software lives by itself in its own world. It has to connect to the real one. I had a hard time finding where to take this talk, where to take it from this point. So it took me some time to figure out what to talk about from here. On one end, I could have chosen to talk about why Erlang does the thing it does, answering the why things are done in a certain way. That will lead us in another philosophical discussion. So I want to go back to the real world now and talk about how it does the thing it does. If you're interested in the whys, we can talk later. The first thing that I said is that in the first part of this talk, I was rambling about like how we should connect the real and the abstract world. How do we do that really? I said the scientist would create models, advanced models. The engineer would deal with failure and quantify errors, right? And Erlang's answers to this is what I call a duality in abstraction. So Erlang provides you with two abstractions. So unlike many programming languages, I mean, I'm simplifying here, but unlike the the mainstream systems we have here, Erlang provides you with two very orthogonal abstractions. One that is meant to represent the real world, one way of looking at it, and the other one that is meant to represent the abstract world. And it is in the abstract realm where you write your programs. Traditionally, these programs have been written in the Erlang programming language. Yep. But over the last few years, we have seen like more and more languages that allows you to target the same environment. So like Elixir is one of them, LFE. There's Gleam, which is statically typed. It is implemented in Rust. I love that. Targeting the Erlang world. And in this realm, the realm of the abstract, you're supposed to just write your programs in the most boring way. I use the word world too much. They're meant to be sequential. There's some loops. There's no concurrency. There's no threads. There's no colored functions. There's no sync versus async. There's none of those complicated things that make our life difficult. Those things that we need in our world, in other software environments, because the real world is complicated. We need those things. Erlang said like, well, those things, they don't belong into the abstract realm because that would be way too complicated. It's possible, but too complicated. It goes on to say one more thing, which is that these programs that we just wrote, they have to run in complete isolation. Again, our abstract world has to be contained. And by isolation, I really mean isolation. Erlang programs don't share memory. That's the first thing. So you have programs, each one of them has its own memory. Implementation-wise, it means that each one of them has its own heap and its own stack. One more thing is isolated in there, which is errors. So the errors are encapsulated within that bubble. So each one of these bubbles is meant to kind of represent a process. That's basically how an Erlang system is. Like a lot of these, like millions, literally millions. And each one of them running a small sequential program. It might be a loop, it might just do something and then terminate, it doesn't really matter. What does that really mean? It means that because they are independent, they're completely isolated. Each one of them has their own memory. It means that we can just like, oh, this one, we can just terminate it. We can terminate any of these processes at any time, whenever we feel like. Last time I had to do some C++, that was like 6 months ago, so it's not that far away. And I had to use some threads. I had to pass down stop token or cancellation token or whatever it was called to try to make sure that all these threads will terminate the right way. Maybe I did the wrong way, I don't know, but that basically was apparently the right way of doing it. You pass down a token and ask, can you please stop? No, I don't want, I'm going to continue doing my stuff. Well, in Erlang it doesn't work like that because each one of them has its own memory, each one of them has its own heap, its own stack, you can just terminate it. We don't have this kind of concepts in programming environments that are mainstream. We have them in operating systems. Modern operating systems work like this. If you use any modern concurrent programming language with, operating system with memory protection, this is what you get. What's interesting here is that the moment one of these programs deviates from reality, now I'm linking again to my philosophical view of the world. The moment one of these programs deviates from reality, which means it's no longer congruent with the real world, you just terminate it. And that can mean that, for example, Erlang programs, they tend to be written in assertive style. So you don't say, open this file. You say things like, this file is supposed to be opened, conceptually speaking. Most of the time it will work. Except when, the file was on a floppy disk, I guess, and the guy pulled the floppy disk and it's no longer there. Or somebody changed the permissions and it's no longer openable. That means that your vision, the program's perception of the world is no longer aligned with reality, so it just gets eliminated because it's no longer true. So reality wins. Or for example, let's say that these processes want to talk to each other. You can say, if I don't get a reply, I expect a reply within 5 seconds. It's not your fault. You didn't get the reply within 5 seconds. We terminate you. And this brings me to the next point, which is communication. So to make all of this useful, Erlang processes, they talk to each other. They communicate. And they do this by sharing messages, sending messages, receiving messages, which is kind of like, when this was conceived, this was like in the 80s, right? It went, again, the opposite way of what other programming languages chose to do for performance reasons, which is to share memory. I'm here in front of you talking to you guys, right? I'm not plugging my brain and exchanging ideas. We don't have a shared brain. I just communicate through a medium, and then you try to internalize these ideas. I'm trying to create a mental model of things. That's really what I'm after. I'm trying to bring you into another community through hopefully a shared socio-technical imaginary. That's really what I'm doing here. And every time I try to replicate this style, it's doable in other programming environments. The thing that annoyed me the most was the communication. Because you have to deal with things like serializing, deserializing, connecting, buffering. What happens if the connection drops? So every time I felt like I was reinventing plumbing, right? A lot of, again, a lot of systems, the ones I've seen, right? I'm not saying a lot of, I shouldn't say that, but the systems I've seen, many of them industrial systems, they would tend to use a broker, a queue somewhere in there. Like, I'm not talking about embedded systems right now. I'm talking about like more like cloud style things. They would put a broker in between that would allow them to send messages and queue them. One of the most famous one is RabbitMQ, if you guys are familiar with it. No? Yes? Yeah? Well, that is Erlang. For the ones, if anybody went and checked the code of RabbitMQ, what is written in is Erlang. Because it makes these kind of things rather easy, really. And what I mean by communication is that it's not just about sending messages. And this is an important bit. What we're talking really about is about sending signals between these processes. Has nothing to do with the Unix signal term definition. It's just about, signal is a generalization of message from my perspective. It's like, it can be a message, it can be some other things. And that brings to the next thing. Like among this family of messages you have this idea of, you have a group of meta messages that are part of Erlang. These messages allow you to do kind of like some bookkeeping, some plumbing that Erlang does under the hood. You just don't see it. And it's used for many different things. And there is two of these special signals that are, there's more, but there's two families that allow you to do something rather interesting, and that is the idea. One of them allows you to do something called linking. Linking is, again, another process I haven't seen in other systems. Correct me if I'm wrong, grab me after the talk, you can teach me, I want to learn. Linking is this rather absurd idea that, let's say we're all walking a tightrope together, like this small tightrope, and we decide to put a rope around our waist. So if one of us falls, everybody falls. Linking allows you to do that. So basically, sometimes, even though I said like processes are supposed to be isolated, that if one of them terminates, it shouldn't induce the termination of another one, sometimes that's not what you want. You want the exact opposite. What you would do there is to link the processes. They are part of a group. They're linked together. And this is a transitive relationship. So basically, if A is connected to B, B is connected to C, it means all of them are part of the same linkage. This relationship also can be asymmetrical. Can you imagine where that would be useful? No. No, both of them would be, if one of them crashed, you kind of want the other one to, no, not really. Yeah, server client would work actually, yeah, absolutely. But it's used a lot in Erlang. It's a pattern that's kind of like codified in the standard library of Erlang that we call OTP. Historical reason why it's called OTP, but that is the standard library. And it's used for building something called supervision trees. So the idea here is that you would create an asymmetric relationship, an asymmetric linking relationship. So you have a supervisor and you have a subordinate, or a worker, as we call it. If the subordinate terminates for a reason or another, because it crashed, because it failed, the supervisor should know about it, but it shouldn't crash itself. But if the supervisor terminates, there is no coordination anymore among the workers, among the subordinates. What you want to do at that point is that all of them should crash. Where am I? Here. Yes. Why are supervision trees? So this is basically how you would see them in an Erlang system. They're always like trees of like supervising each other. And why would you want that? Because as it turns out, it's rather difficult, I would say borderline impossible, to handle an error internally, like a real world error, because you don't know. The thing is, the moment a program fails, like let's say this one over here fails, first one, why did it fail? It failed because it's no longer, its vision, its view of the real world no longer matched that of its own. They are no longer congruent. They basically diverged in the way they perceive things. How is it supposed to recover from that? Well, if it had the code for it to handle that particular situation, it wouldn't have crashed. So it crashed because it had to deal with what we would call an unexpected situation. And the idea here with the supervision trees is to create failure domains. So you have a tree of supervisors and workers, And whenever a supervisor, whenever like kind of a worker fails, the supervisor will get notified. Then the supervisor has to do something. And that's codified in the structure of your system. This is the external Erlang, the second abstraction domain I've been talking about, where you say, well, if that one crashes, restart it. Or you can say, if that one crashes, terminate all the siblings and start over again. Or you can say, if the third one crashes, I want you to crash whatever comes after it because there's a relationship, an ordering relationship between them, and then crash all the ones that come after it and restart from there. And if that fails, escalate. So if the supervisor itself fails to handle this situation for a reason or another, because it loops, for example, or because things are just too messed up, it just escalates and then it goes on and on and on. When it reaches the top, your system terminates. Again, it all depends on how you put it. Like if you put it inside a Linux service like systemd or anything like that, then systemd will restart it. If on the other hand you decide, well, I'm gonna put this as init1 or pid1, then which some people do, then it means that when your system, your Erlang system crashes, and if you configured your kernel properly, your Linux kernel properly, it will just reboot. Some people put this stuff on microcontrollers. That's another family of Erlang VM implementations, but I haven't really worked with them. There's 2 of them, but that's another story. So, as I said in the beginning, this talk is still work in progress for me. It's like a lot of my ideas and my thoughts are still not coherent. I'm just hoping to share with you, and I would like to hear your feedback. But before I move on, I would like to talk about those extra bits that I didn't have much time to cover here. I skipped some things just to make it a bit lighter. So one thing is that distribution comes naturally from this. There's like a feature you might have heard of, but essentially Erlang takes the idea of failure even one step further and say, well, I mean, your hardware can fail. So what do we do about it? Well, you just replicate the hardware. Make 2, 3, 4, 5 copies of the hardware running your software. Put them together in a box, and then if one of them fails, the other one takes over. And this is rather easy to do in Erlang because we have this isolated small processes. We have this mechanism that allows you to supervise and monitor and check if things are failing. We can be notified if, for example, we lose connectivity with the other node. We have all this mechanism that allows us to do that. The second one that you might have heard of, I don't know, is code upgrades. So the idea here, Erlang was born in the telecom world where basically they had this requirement for uptime and availability. So they had to upgrade the system while it was running. So they couldn't just unplug it, update the firmware, and plug it back in. Nowadays, at least in the Erlang community, not probably within Ericsson, is it's not very much used. It's because it's hard to use in the clean way. You can do it the dirty way, but it's relatively something that if you can do away with, you just do away with. In my personal experience, I have had to use it. So a few years ago, that was 2012, I think, I was part of this, founding this startup doing music listening, shared music, live music listening experiences inside Spotify. And one of the things we did was basically to have this online events. So we'd invite artists. We had some really big artists coming in our platform, listening, interacting with the fans. I still remember really, like as if it was just yesterday, we had this colleague in the US who was like, yeah, you guys can just go home. We have this artist event starting at 7 p.m. Oslo time. I used to live in Oslo back then. But it's an artist nobody really know much about. I mean, it was Kendrick Lamar. For anyone who is into music, it's a relatively big artist now, but back then very few people heard about him. And then I was sitting there 6:30 p.m. still at the office, just like, and I see my charts, my graphs like climbing up little by little. They were not going down because this guy was bringing, I think like it was 16,000 people on one single node that they had to connect to. And what was causing the problem is that we had a chat functionality. People would chat and talk, and people were so engaged that they would just spam the server, like really going crazy at it. What we did in a hurry, we patched the server while the system was live because we couldn't take it off. The artist event was about to start. We just patched it, made it work. We implemented a rate limiter for the messages that come from the client regarding chat. Each one of these processes, there were like 16,000 people connected, so there were like 16,000 processes. Each one are representing one connection. That's how it worked. So we just upgraded the software, and then everything went fine. Same thing happened another time, but we didn't manage to. That was with the artist called Demi Lovato, and I'm still angry about that because she crashed, or her fans crashed our servers, and they were really proud about that. They went on Twitter like, yes, we crashed this platform as well. The other thing is soft real-time. So the Erlang runtime system is soft real-time for a definition of soft. And that comes natural because like each one of these processes, they're meant to be small. Each one of them has their own heap, their own stack. Each one of them has a garbage collector. And the garbage collector is deterministic. It only runs when you run out of space. So you could kind of predict with some amount of effort how the whole thing is going to behave. The memory implementation is rather interesting. You have a stack and a heap, and they grow towards each other. And the moment basically they clash is the moment basically where it triggers a garbage collection. It has a load time JIT. And I said load time because it's not runtime, because this soft real-time aspect, this predictability aspect of the system is very much valued in the Erlang community. We wouldn't want a system that is slow and suddenly becomes fast. We want a system to behave consistently. So for x86-64 and ARM64, you have a JIT. So when the code is loaded, it's compiled into native code at load time. There is another function you might want, if you're interested, I'm just giving you pointers here to things to look at, right? Like ports. This is a nice way, external ports, they are a nice way for integrating your external existing programs, C, C++, Rust, Python, whatever you want, into the system in a fail-safe way, in a fault-tolerant way. Each one of these things will kind of behave like an Erlang process. Behind, they are typically implemented as an OS process. So you have the overhead of an OS process, but that's not a problem in the Erlang realm. That's something you have to deal with outside. Then you have NIFs that you might want to look at, which is native functions. I'm talking to you as C and C++ programmers. When ports are too slow, because there is an overhead of communication, you can plug in a native function into the VM at your own risk. So if it crashes, but if you build like a lot of VMs and supervise them properly, you should be fine. The VM is rather small. I got that question yesterday. It's really small. I mean, we shipped like, since 2016 in my company, we helped customers ship like 2 embedded Linux systems, Erlang based. So this was embedded Linux, yeah. So Erlang based. I think the entire system image size was about like, typically 30, 40 megabytes, including everything, like including kernel, including the Erlang VM, the Erlang code, everything you might need. And we didn't even put any effort into optimizing because there was no point, really. There's a yearly major release. So we're at 25 right now. So every year there's a major release, followed by 3 minor releases every quarter. And there is a backward compatibility support for 2 versions backwards. So it's always basically, yeah. You don't have to be on the bleeding edge. That's what I'm trying to say. And with this, I really want to thank you for joining me here today. I really hope that I managed to share some of my thoughts with you. I know some of them were a bit heavy, and I'm very sorry about that, but I'm hoping just to open a bit, like to just open the conversation. If you have any questions that you'd like to raise, please, I think we have 4 minutes, right? So please go ahead. Otherwise, if you feel that basically that's much more of an email thing, my email is here, so you can send me an email. I'm really happy to converse about any of these thoughts. If you're wondering about like how we build and ship or shipped Erlang systems in real life, in production, you can talk to me. That's basically it. Any questions? Yes, please. Yeah. You mean microsecond, right? Yeah. I mean, typically microsecond, nanosecond is basically where so basically there is different ways of looking at things. It all depends on your program, of course, like any real-time system. So if you write something that is strange, then it's your problem, right? The good thing is, let's say basically with this isolation, I mean, there's many things that when you put together, it makes sense. These programs, they run in isolation, which means an infinite loop in one of them just does not affect the other. It has no way of slowing down the other. There is real isolation between them. The memory, if you write your program, if you spend the time, because normally there's only one bit of your system that you really care about being real time. You don't care about the entire system. You care about this part being real time. In at least the systems I worked with, maybe I'm wrong. Maybe I mean, I have the experience I have, right? And you can focus on that bit, on that process. Give it enough memory from the start, so it basically just doesn't, it never needs to garbage collect. Then you're good to go. Yeah, then you're fine if it's millisecond. I know basically that, for example, there is a project called GRISP, where basically they have a kind of a fork of Erlang, where they are targeting their own hardware. It's called a GRISP board, which is an IMX board. If you're basically they are doing a hard real-time version of Erlang there. They take Erlang and they compile it together with RTEMS or RTMS, I guess. I'm not familiar with it, so I don't know. And just they use it for, I mean, last talk I was in Stockholm a few months ago, and they were using it for conveyor belts within the factories of Bosch in Germany. So that's the kind of stuff. It's like there's like a lot of Erlang out there. You just don't hear about it. Any other question? Please go ahead. Yes, no? Okay. Well, thank you so much, and you have a very good rest of the day, and hope to see you again.